Welcome, everyone, back to the American Museum of Natural History on this auspicious day, 10/10/2010, the day we've chosen to celebrate the 10th anniversary of the opening of the Rose Center for Earth and Space. Some of you were here earlier with the festivities. We had a huge cake. We had live entertainment. We gave out awards for the best video. We had a video contest. The best 2-minute expression of what science has meant to you for the past 10 years. And so if you go to the Rose Center website, you can see the award-winning videos. The runner-up video I like to characterize as, are you smarter than a 2-year-old? Because in it, there's a 2-year-old reciting all kinds of cosmic phenomena and names of things. And it's a remarkable video. It's gone almost viral on the net, so check that out when you get home. This is a specially inserted Asimov panel debate. Normally we meet in the spring for this once a year. How many of you are sort of regulars to the spring one? Excellent. And who here is the first time you've ever been to an Asimov debate? My gosh. Where you been? What? So, welcome to this one. We'll be doing this again at our usually scheduled time in the spring. Follow the news announcements for that. For this occasion, we thought we would involve a few more geologists and answer a fascinating question that's been on our minds for a long time, many people's minds. Is Earth unique? Is Earth unique? Now, we don't mean exactly unique. Obviously, any planet is unique down to its details. So we're really asking, are the general properties of Earth something we can expect to be common in the galaxy or rare? And that question does not have an easy or well understood answer at this point. Hence, we make it a subject of this debate. And interestingly, what happened just a few days ago in the news? An Earth-like planet. A Goldilocks planet around star Gliese 581. The star is Gliese 581. There are several objects already known to orbit that star, the most recent of which is a slightly larger than Earth-sized planet orbiting at just the right distance, which if it had water under an atmosphere, it would remain liquid. Too close to your host star, it evaporates. Too far, it freezes. So it's Goldilocks temperature, just right. And on Earth, where there's liquid water, there's life. So water is a tantalizing tag for us as we conduct our search for life in the universe. That's the first of what we expect to be many such planets in orbit around their habitable zone. We have a remarkable selection of panelists. One of them, in fact, flew in from Europe. Another one came in from California, landing just moments ago. And I'll be introducing them in sequence. I have first an astrophysicist. Oh, by the way, all of the bios are in your schedule, so I'm not going to read through all of them. They'll be here for you to see. And I want to get straight on to our panel discussion. Before I do, let me publicly acknowledge the support of this program by the friends and family of Isaac Asimov. He was a longtime friend of the American Museum of Natural History. He used our libraries to publish his 600-plus books, one of the most prolific people in the history of book writing, and on science fiction, science, even wrote books on religion. Not a single subject was beyond his reach. And much of his research that he conducted was here at his backyard museum, the American Museum of Natural History. So we're indebted to the support that the loved ones and friends of Isaac Asimov have provided for these past 10 years. And so first, let me bring out onto the stage right now Fred Adams. He's a professor of physics at the University of Michigan. Fred Adams, there you go. They will each begin with a minute or so of what it is that they do and why. And so we'll wait till we get all 5 panelists out to discuss that. Come on out, Don Brownlee. He's professor of astronomy, University of Washington in Seattle. Don Brownlee. We have Paul Falkowski. He's professor of geologic and marine science at Rutgers University. I just realized you're a pretty cheap date. You just came across the river here from New Jersey.
I can charge more.
We'll have to invite you more often. And where am I here? Who did I leave out? Yes, thank you. Chris McKay. He's a NASA scientist working at NASA Ames Research Center in Moffett Field, California. And we have Minik Rosling. He's professor of geology, University of Copenhagen. Minik. Just a half hour ago, we had a conversation in a room in the back, because we all took a look at each other and said, oh, wow, we're all guys, you know? So this did not go unnoticed by us, and we're going to check to see if we've had some inherent bias over the years or what. So we'll be checking on this in future Asimov debates. Yes. Just while we're in demographic statistics, in the whole world of astrophysicists, 36 of them are black, and one of them hosts this, so that's just so that you know. So we're doing good on some counts here, I think. All right. So, Fred, why did I invite you to this panel? Who are you to us today? Just tell me. Well, remind me.
I work in theoretical astrophysics. I work primarily as a theorist, so I do calculations more than observations. I spend my time primarily in a physics department rather than an astronomy department, but I work in both camps, so I kind of bring that to the table, I guess. I've spent most of my time working on star and planet formation. About 2/3 of my papers are in that realm, which is relevant to today's picture, or today's discussion. And then I spend about the other third of my time working on larger scale things, cosmology and related issues, which kind of informs the big picture of what we're talking about.
So you think a lot about the physics of the universe and how that shapes what the universe ultimately looks like.
Yes, exactly.
And is most of your work on computer, or is it just back pencil and pad?
The answer to that is yes. I'm one of the old school people that still do calculations on paper, but as you know, and most people know, eventually you often have to put equations on computers as well. So I go back and forth between the two media. Okay, excellent, thanks for that. Don Brownlee, you're an author of a book, Rare Earth, so you're like the right guy to come in here, but what else have you done lately?
So I'm an astronomer. I work in the solar system, planetary science. I was also head of the NASA Stardust mission that brought comet samples back to Earth. And along with...
I have to interrupt there. I remember a movie where they did that, like the Andromeda Strain, where they brought particles from space. I'm just you were not worried about this.
You would not believe it, but if you look at the movie, the capsule they brought back in that movie was almost identical in size and shape to the one we brought back with comet dust.
I knew it!
and the instruments were very scientific in that movie. They used electron microscopes, mass spectrometers, very similar to what we actually use on the comet sample. It was many years later, although JPL and Caltech were advisors on the Andromeda Strain. But yeah, I'm also an author with Peter Ward, paleontologist, on 2 books. One is called Rare Earth, which is just says the Earth is rare, and is about the rare Earth hypothesis, the idea that life may be common in the universe, but like on Earth, over its entire history, it's mostly microbial, and it takes very special conditions to have animals like us. The second book was Life and Death of Planet Earth, was amazingly the first book about the long-term future of our planets. Some things that everyone should have learned in 3rd grade and didn't about future Earth history.
Okay, so we'll get back to you on that to find out if we actually believe you that Earth is as rare as you suggest. So, Paul, let me get your name pronounced. Fulkowski. I tried. Fulkowski, yeah, tell us what part of the universe you come from.
So my interest here is the evolution and origin of life, broadly writ, but from a concrete point of view, I studied for many years the origin of biogeochemistry, which is, to all of us in this room, we're breathing oxygen that was created by organisms. It's not a trace gas on the planet. So there's an oxygen cycle, there's a carbon cycle, there's a nitrogen cycle, and I study how organisms basically transform the planet to make it livable.
So you're a biogeochemist.
That's right.
You just stapled them all together.
Staple them all together.
Okay. And this sounds like that's an emergent field, because not that long ago, our scientific professions were pretty divided up department by department. So are you a renegade, or at least on the frontier of a trend line that we should look forward to?
Yeah, I'm trained in biophysics and molecular biology, and I'm in a geology department. So you could say it's a trend line that's a little weird.
So you're a one-man cross-pollinating machine. Yeah.
I tried.
Okay. Chris McKay, you flew in. You said you just flew in from California, but I don't think so, because I think you just flew in from Mars. Mars is like your favorite planet, and that's all you ever talk about.
Well,
but for example, you could have like breakfast with the guy, and you're drinking water and eating, and he'll say, on Mars, this would, no matter what you say or do, he references back to Mars.
Right. And it's a good connection to Earth and the question of life. What I'm interested in is there life on other worlds, and is that life different from life on Earth? And in a way, it's asking the question, is the story of the most important thing that we see on this planet, what Paul studies, life, and the biogeochemical cycles that it creates, is that story repeated on other worlds? And if it is, are the organisms that are doing the biogeochemical cycling on other worlds similar to the life forms we have on Earth, or are they aliens?
I'm going with the aliens.
I'd like the alien answer myself. Yeah.
All right. Minik Rosing, I have to tell everyone that you were born in Greenland. That is surely the first person I have ever met born in Greenland. And how many people were in your hometown when you were born?
Well, there's not really a town. There were 7 people, so it was.
A town of 7.
It's about a factor.
We can't even
City, I guess.
think that. We don't even know how to understand that. A town of 7 people.
Well, it seemed quite busy at times, actually.
So what scares me a little is that you're born in Greenland, and Greenland is the subject of your research specialty. And you've done great pioneering work there. It makes me worried, like had you been born in like the Bahamas or something, you'd still be on the beach, and we wouldn't have learned what we have about Greenland.
No, I think actually, had I been born in the Bahamas, I'd still go to Greenland, because it's the most interesting place on this planet. And it's a place where I do what I'm best at. I'm a geologist, and I have to warn you that geology is the only science where your feet are more important than your head. So that's the vehicle you use to walk across the fields and beat on rocks with big hammers, and so that's kind of the level of sophistication I operate at.
Okay, so let's start out with you. Let's start our conversation. So many new hands had been raised. The way we're going to conduct this is, we're not actually talking to you. We're having a conversation like we're at a bar or something among ourselves, and you're eavesdropping on it, okay? That's how these go. You got that? Okay, we're just chilling up here on the stage. So Minik, we're trying to understand whether or not Earth is unique, but you work in Greenland, and there's nothing more foreign that I can think of than Greenland, especially since it's mostly ice, so it's like badly named to begin with. Mm-hmm. How could studying Greenland possibly inform the rest of this conversation about Earth?
Well, Greenland have preserved the oldest part of Earth. So we have rocks in Greenland have experienced 3.8 billion years, 3,800 million years of Earth history. And that actually is almost 1/3 of the existence of the entire universe is recorded in these rocks.
Wait, so why are your Greenland rocks older than somebody else's rocks?
Well, because we found them there. There's no logical explanation. It's just the way it happens to be.
No. So is there some geological fact about Greenland that enabled it to keep older rocks compared with some other place on Earth?
Not really. I think the magic point about Greenland is that it has been glacially polished within the last few thousand years. So that means that the rocks are not covered by soil and plants and other ugly things. So you can really see the geology, and that allows you to get a much deeper insight into how the geology of Greenland is put together. And that allows you, again, to find the really interesting rocks.
So you're saying when you say glacially polished, so a glacier works its way, it's very heavy and deep, and it just sort of carves its way over the surface. And then if it retreats, it's kind of a freshly exposed...
Exactly, yeah. If you try to do that in Arizona or someplace like that, you see a lot of yellow sand and more yellow sand and more yellow sand. In Greenland, you have pristine rocks, and they're just sitting there for you. So that's the marvel of the place.
Okay, no, I never knew that about it. That's very good. Mm-hmm. And actually, I think could you switch places?
Don?
Yeah, I'm sorry. It just...
Good luck.
There you go. Thank you.
Oh, this is much better.
So, Don, what are your best arguments for whether or not Earth is unique? Are they philosophical, or do you have real science behind these claims? Because I read your books, and you make some interesting points. And when you say unique, is it rare because of the life that's on it? Surely you agree that maybe other planets have oceans, so where are you coming from?
Well, the Earth is undoubtedly rare. I mean, it's rare in the solar system. It's totally different than any other place in the solar system. Look at this from an astronomical standpoint.
Well,
Lots of people...
Wait, the solar system is this big in a galaxy that's this big, okay, and you're asserting that it's rare.
Think of the universe in a whole. You can do that. A lot of people like to think of the universe as being a very friendly place. It's almost an incredibly, totally hostile place.
I agree 100%.
There's only a couple places where we could go and live. To me, Earth-like means if I was there on this other body, I'd feel at home. And I could go and breathe this rich oxygen atmosphere and be happy and look out and see palm trees and beaches and people running up and down the beaches, or something running up and down the beaches. And you know, our neighbors in the solar system are vastly, vastly different than we are. I remember...
You mean Mars and Venus are adjacent planets?
The whole rest of the works. You know, I remember when the hijackings probe landed on Titan, a big moon around Saturn, all the comments were, boy, this is really Earth-like, because it has liquids, it has land, and it kind of
had coastlines. It had
coastline. It looked like Louisiana, you know, when you fly over Louisiana. But it's only a little bit warmer than liquid nitrogen, and you would feel less at home in Titan than you would in Mars, which is a really unearthly like place. So there are lots of places in the environment.
Be careful, because he's going to fight you if you talk bad about Mars.
I mean, so anyway, the Earth is rare to other places in the solar system, and the Earth we live on now and think of our Earth is actually not typical for the Earth throughout its entire history. Earth will last about 10 billion years, and yet it took 4 billion years of geological and biological evolution on our planet to get animals on it. So, you know, what is Earth like? Typically in the past, you would land on Earth, you'd look around, hey, nothing here, let's zip off to Alpha Centauri or something. Even though there was life on Earth for most of its lifetime, it was microbial. It wasn't animal life. And the Earth will spend at least half of its entire lifetime as an ocean-free planet. And most Earthlings right now, you look at that planet and say, God, that's not an earthly planet. There's no ocean. It can't be like Earth. Well, it is Earth. Earth has changed a lot over the past.
So you're saying Earth isn't even like Earth for most of Earth history?
Yeah. I mean, Earth, most likely, when it was very young, was a water world, completely covered with water. I mean, you know, we don't know what it takes to support life. We know what it takes to support us. And we can't live anywhere else in the solar system. We can't live on Earth as we are right now during most of Earth's history. I mean, more than 2.4 billion years ago, there was no oxygen in the atmosphere, so we would asphyxiate, just gas, gone.
Although the anaerobic microbes were doing just fine.
Microbes are tough, much tougher than we are. But we're smarter, so we in the end, we may beat the microbes, believe it or not.
So we tell ourselves constantly that we're smart.
We live in an artificial environment.
I read the paper every day. That's evidence, counter evidence to...
No.
So, Paul.
Yeah.
one thing that I think is not widely appreciated by the public, and perhaps even by other scientists, is how many cycles are going on simultaneously on this very Earth in which we live. And for me, what impressed me most, I think, was to realize that if you're going to look for another planet out there in the galaxy, the urge is, well, let's find a planet that has a nitrogen-oxygen atmosphere as we enjoy here on Earth, and then that's where we'll pitch tent and live. As though that's the kind of atmosphere that you just might randomly find among planets. But of course, life infuses the atmosphere with these properties, and life affects the oceans, so that we're not just living on a planet, we're a participant in the planet. So tell me about some of the cycles that either we contribute to or that affect us directly.
So life is made up of 6 major elements: hydrogen, carbon, oxygen, nitrogen, sulfur, and phosphorus. And all of these cycle. And the cycles to first order are driven on this planet by tectonics, because the Earth's interior has uranium, thorium, and potassium, and there's radioactivity. And that allows the mantle to cycle. And it brings, for example, through volcanoes, CO2 into the atmosphere. That's why we have CO2.
So we need our volcanoes for this cycling.
Absolutely. Without
as bad
volcanoes,
and menacing as they are, they're a fundamental part of these cycles.
Absolutely. First order, fundamental part of the cycle. The carbon dioxide that's in the atmosphere absorbs water. It makes carbonic acid, which is like seltzer. Seltzer rains on igneous rocks like granite. And the igneous rocks, so-called weather. So magnesium and calcium are taken out of those rocks by this weak acid, and you form chalk. And so that's, to first order, the carbon cycle.
So chalk is a repository of the carbon.
Exactly. And so that cycle, which is dependent upon the weathering of rocks and volcanism, has maintained a carbon dioxide concentration that has not led to a runaway greenhouse like on Venus, or has not collapsed totally like on Mars. So the amazing thing about this planet is it's a Goldilocks situation, where tectonics stopped on Mars, and it lost its atmosphere. In Venus, it's incredibly, incredibly warm. There's huge amounts of CO2, and it's much too hot for life to exist as we know it. And Earth is the only one that is within the so-called habitable zone where liquid water could exist, where there is actually physically liquid water on the planet. And it has nothing to do with us. It has everything to do with just this volcanic activity and rock weathering. So
when you say cycling of the land, you're talking about continental drift, where the crust goes down,
right,
gets reheated, and basically comes out of a volcano somewhere.
In this case, we're talking about sedimentary materials from the oceans primarily. Yeah, right. This is marine sediments, the marine crust, oceanic crust going down, underneath, subducting, in this case now, underneath the cratons, the continents, and coming back up in volcanic material gases in the mid-ocean ridges and to some extent on land, but the mid-ocean ridges primarily. So that's one cycle. And then there's a nitrogen cycle. The natural nitrogen cycle is dependent upon an oxygen cycle, and the oxygen cycle now is dependent on life. And all of these cycles are intertwined. So it's not as if one cycle operates freely. They all are related to each other like a network of wires in a circuit diagram. And understanding the feedbacks here is not easy, and it's one of those things that we really don't understand very, very well, frankly, in science, because we don't have experimental planets where we could go out and say, oh, let's kill off all the nitrogen fixers and let's see what happens.
Well, no, we're already experimenting on Earth. That is our experimental planet. Last I checked.
We're experimenting with ourselves. So Don may say that, well, what are we doing here? I would argue that what we do is carry E. coli around from place to place and deposit in different places. So we are basically a vector for
We are vessels for bacteria.
Vessels for bacteria.
Yeah. I once looked this one up. We have more bacteria living and working in 1 centimeter of our lower colons than the total number of people who have ever been born.
Exactly. Right.
So in terms of who's in charge, they would have a different answer to that question than we would.
Right,
yeah.
Exactly.
Yeah.
2.5 kilograms approximately of each of us is bacterial.
That's just a nasty thought. Right, we have bacteria all on our skin and in our digestive tract.
Everywhere. Right. You are not who you think you are.
Creeping me out. Chris, Mr. Mars, did you really just fly in from Mars?
No, I just came from JFK.
From JFK, okay. Just had to clarify that. Let the record show. So how does Mars fit into this? You know, we've all seen, perhaps, images of Mars, and they're tantalizing. You see dried riverbeds and river deltas and floodplains, and water clearly had a significant presence there. And we like water. We think of life when we think of water. The place is bone dry now. Something bad happened on Mars. So do you, apart from your interest in finding life there, maybe subterraneously, is there some lesson that you can learn from Mars that will apply here to Earth? Because I think we want to keep our water.
Yeah, the general lesson of take care of your planet is a good lesson. And we might learn that lesson by studying Earth, obviously, but also including Mars in that study. But the more important question I think we're asking about Mars is the fundamental question about life. As everyone here has been talking about, life is all over on this planet. It's done amazing things. It's continuing to do amazing things. We eat it for breakfast, lunch, and dinner. It's an important part of everything we think about when we think about Earth. But we don't understand whether that phenomenon is unique to Earth or has occurred many times in many different places. Mars is our first chance to really test that, to really go and look. This planet had water for a long time. It was kind of like Earth. Did it have life? And if the answer to that is yes, it had life, even if they're all dead, and that life turns out to be different than Earth life, what I call a second genesis, that's really cool.
Different as in no overlapping DNA, or whether it has DNA at all?
Well, different if it has a separate origin. Even if it's got DNA, if we can deduce that it represents an independent origin of life, so that right here in our own little solar system, life started twice, that's telling us some amazing things about the nature of the universe.
So that would say that life, that Mars, that Earth, in fact, would not be unique. Right. That if one of our closest neighbors had these properties at some time in its past, then we're good to go. Water, a little bit of atmosphere.
Yep, it means the universe is full of life. And that we have every expectation that we find other worlds around other stars with water. Even if they don't have all the plate tectonics and things that keep them active for a long time, they still have a chance at life. Life becomes then a natural feature of the universe, not a quirk of some odd little planet around this curious little star.
I like that. Okay. Fred, you think about the formation of solar systems and of planets. And of course, you were never there, so you have to sort of apply the known laws of physics, look at examples in our galaxy where planets are forming. What have you concluded about planet forming in general, but our solar system in particular?
Well, there's a number of things you can say. One of the first things that we found circa 1984 is that when every star forms, it forms with a circumstellar disk around it. This was something that Kant and Laplace had predicted 200 years ago, but no one had actually seen until the 80s.
Circumstellar disk, you mean you make the star in the middle and there's extra stuff that forms a platter.
There's extra gas and dust surrounding it, in orbit around it. And the remarkable thing about these disks that we found in the 80s was that they have the right mass and the right size to form solar systems. Before these disks were discovered, people had done the exercise of taking the planets in our solar system and augmenting them with extra mass, extra gas to make them have solar composition so that they would have the same composition as the sun, and then they would deduce the properties of the nebula that our planets formed out of. These disks have a range of properties, but pretty much exactly what we would have predicted. So the birthplace of planets were predicted and seen and measured in the 80s, which argues that things are ripe, conditions are ripe for planets to form. Then in the 90s, we found planets around other stars. Right now, there's anywhere from 400 to 800 planets, depending on how you do your accounting, that we've discovered orbiting other stars. And the number changes every day. Since I haven't checked the internet for a couple of hours, there's probably more. In fact, at 10 o'clock tonight, there will be more preprints on the Astro PH preprint server and probably an announcement of another planet. So there are planets everywhere.
Wait. There is an exoplanet app for the iPhone.
Oh, there is. I
Yes.
don't have that app.
Yes, yes. And so it has all the properties of all the exoplanets, and every time you update it, it gives you the latest file on it, and it shows you the orbit, and it's pretty, just look it up.
And it beeps you at 7 o'clock in the morning, too.
It's what you say?
It beeps you at 7 o'clock in the morning and tells you there's a new planet.
I don't mind that. I'm cool with that.
But anyway, if you take the observed sample of extrasolar planets, and you have to do a bit of an extrapolation because we haven't looked at every solar system for as long as we would have liked, but you can deduce what fraction of those solar systems have planets. And that projection gives you anywhere from 20% to 50%. What that means is that anywhere from 20% to 50% of the stars out in our galaxy, or at least in our solar neighborhood, have planetary systems of some kind. So that bodes well for looking for Earths.
This is like the Drake equation, where you look at the probability of a star that has planets, that has a planet in the zone.
Yeah, this is exactly one part of the Drake equation. For those of you who don't know, the Drake equation asks the question, how many intelligent civilizations are there in a galaxy? And in order to get up to an intelligent civilization, you have to have a number of factors. You have to have stars, you have to have planets, you have to have the planet have life of some kind, you have to have animal life, as we've seen. Then the animal life has to somehow become intelligent, which may or may not have happened here. But then it also has to have technology in the Drake equation. So we're a long way from being able to predict the last of those factors. But one of the things that's, I think, very satisfying is that the astronomical part of the Drake equation is rapidly becoming coming into focus.
Yeah, so a solved problem at that level. Yeah.
And it's being solved in the positive direction. Yes, there are solar systems. Yes, there are planets. Yes, there are places where life could, in principle, arise.
I would go further than that, if I may, because let me get back to you, Paul. You gave a list of, both of the two of you sitting together here, each would leave us to believe that what we see here on Earth, because of all this interplay of cycles and conditions and circumstance, it's as though A has to go to B to C to D, and we're like Z in this sequence, and if you break any of these chains, something bad happens and we don't show up, or something catastrophic happens to the planet. But let me ask you, practically every time we have imagined that something was a special condition, upon further exploration in the universe, it hasn't been. So for example, even in the Drake equation, where they talk about the habitable zone, before we call it we would only later call it the Goldilocks zone, the habitable zone, we have one of the moons of Jupiter, Europa, kept warm not from the sun, but from the gravitational stressing of Jupiter and the surrounding moons themselves. So,
in fact, there's another way to do it as well. If you have a planet as big as the Earth that lives in the outer solar system where the moons of Jupiter live, the natural radioactivity will keep liquid water pockets. They won't be on the surface, they'll be beneath ice sheets. But
so the
liquid
undersea
water.
vents, that's a source of energy, nothing to do with the sun. Life could just be doing the backstroke down there and won't even care what's happening on the surface.
Yeah, well, what we know for sure, or what we think we know, is that there will be liquid water and there will be an energy source. The rest is what we're debating here.
So what I worry about is, couldn't there be other combinations of cycles that would still work for some kind of life that we might not have dreamt up yet?
Well,
and if that's the case,
yeah.
You could say Earth is unique for us, but unique for any kind of life at all, maybe not. Because you haven't thought of these other ways, because nature can be inventive at times. And it's typically more inventive than we ever are. So how do you address a criticism that you just haven't thought of other ways to sustain a planet that could, to create a planet that could sustain life?
So the way biologists have looked at it over the last 20 or 30 years is they've looked at what's called redox couples. That means the difference in energy between, for example, hydrogen and oxygen. And that redox couple is very large. And obviously, everybody in the room, let's do the following experiment. Just take a breath. Okay, so you just exchanged hydrogen from your body with the oxygen in the atmosphere, and the primary gas which resulted from that was water. Okay? So that's a very, very high energy gap, which allows us to derive a huge amount of energy from that reaction. That reaction is a relatively recent reaction. It only happened about 2.3 or so billion years ago. Before that, the reaction was constrained to hydrogen sulfide or iron oxidation. So those reactions have much, much lower free energy. And it doesn't matter what planet you're on, you're endowed with a certain number of redox couples. So on Europa, the only reason you could have life in the interior of Europa is either because something is supplying a redox couple from the interior of that moon, or there's a subduction of ice from the surface into the interior, and it cannot be a closed system. And all systems ultimately have to be open systems. So what I'm saying is, in our case, we only make bond energy, new bond energy on this planet to first order, because the sun is shining and something is taking water and splitting it, which we don't do, splitting the water, and creating energy gap, and using that hydrogen effectively to reduce the CO2 in the atmosphere to sugars that we eat. So those are really common metabolisms.
So in fact, correct me if I'm wrong, the main engine on the space shuttle, the big orange engine, is a hydrogen-oxygen reaction.
Absolutely.
And so it's just making water as its exhaust, and it's exothermic,
right.
And the thing takes off.
Right. You and I are fuel cells. We're just a much more controlled rocket.
I think you could also add that if you go towards the intelligent life, you can say that our brain uses a quarter of the energy that our entire body consumes.
Exactly.
And that means that you need a very intensive source of energy if you want to be intelligent. So if you should sustain yourself with the thermal energy inside a moon someplace, there's no chance that you could organize higher organisms on that feeble amount of energy you have there to that level, I think. I think that we are so dependent on being able to convert the energy from the sun into something that we can use to sustain a high level of activity.
So there's still more intelligence in Louisiana than on Titan. We can be sure of that predictably.
Yes.
He can pull off that joke here in New York, but in Louisiana, just try that in Louisiana, I think. I think they just passed a law that you have to carry a gun, so you'll have a different reaction down there. What do you have to say about what they just said?
Well, I have a more optimistic view. And
That's why I came to you.
yeah, I think we should look for strange things and hope to be surprised. And the strangest world that I think is promising is Titan, because there's a liquid. And on Earth, we know that life is tied to liquid water. We don't know if the critical thing is the liquid or the water. And on Titan, there's a liquid. It's the only world in the solar system with a liquid on its surface besides the Earth. The liquid's not water, it's liquid methane. But in many ways, liquid methane is a nicer liquid for life than water. Water's aggressive, it tears molecules apart, it's at high temperature. There's a lot of drawbacks to living in water.
But methane is the gas that comes out of my stove.
Yeah, but on Titan,
that I ignite and cook my food with.
That's because we have a world that's hot with oxygen. On a suitable world, a world that's really built for life, the temperature is very cold, so things can move very slowly, and methane is a liquid. It'll look just like this, clear, and if this was Titan, it would be stable, it would be a liquid, and you could imagine a biochemistry based on that liquid. Finding that would be very, very interesting.
This is way outside of any box that they've been talking about right
exactly.
here.
It's not just outside the box, it's on the other side of the street. And that's what makes it so interesting. If we can find life that's that strange, then we know the universe is really full of interesting creatures.
So
I had an incident.
Yeah.
I was interviewed on Charlie Rose. This is now 15 years ago when the Mars rock story hit. You remember that?
Sure.
The Allen Hills Mars rock, a meteorite on Earth discovered to have come from Mars all by itself. It was studied for the chemistry in the nooks and crannies, and there was some curious properties of the material that was in there that was suggestive that maybe it was life. Then they showed the picture, that little wormy-looking thing, and that was not ever advanced as evidence for life, but it was just a curious photo. In that interview, there's a biologist piped in, and he sees the picture and said, "That can't possibly be life." I said, "Why not?" And he said, "That's only 1/10 the size of the smallest life on Earth." And I'm still waiting for him to give the reason why that can't be life, but that was his reason. And then I said, "Last I checked, this is from Mars, so why is Earth your measure of this?" And so I wonder whether biologists are sort of, harping back to his point, I wonder if biologists are kind of stuck in their sample of one. And the sample of one is all life on Earth has common DNA. You don't have another
that's-
example.
No, that's not the story.
What's the
it's
story?
The story is that you have to, if you're going to have life, you have to have two properties. You have to have self-replication, you have to have a metabolism.
How do you know this?
Well, otherwise, how do you define it?
That's what. That's not an answer to what's the definition of life. You give me that comment, and then you say, well, otherwise, how would you do it? I guess
What
what
would you, and you went to Titan and you found, what would you look for? If it's not replicating and it has no metabolism, what is it?
Okay, so now if you define it that way, and then you find something else that's not that, well, what do you do with it?
It's called a mineral.
But you can.
Oh, called the mineral. Oh, okay. It's a rock, Jim. Okay. So we have words for things that don't do that already, is what you're saying.
Right.
Yeah.
I mean, I can plug my computer into a wall, and it has a metabolism of a sort. So there's an energy supply to it.
Yes.
It doesn't replicate yet. So
Stars have a metabolism, and they're self-replicating. Is a star alive?
no, they don't have a metabolism in a sense.
Yes, they do. They have
What
an
do you mean
energy
they do?
supply. That's an energy supply.
Right. But they're not Darwinian. They don't reproduce, mutate, and then are selected by an environment.
That's a
what
very
Paul's
earthbound
getting at.
statement.
Well, I think it's a more general statement, and that's what we'd be looking for on Titan. We wouldn't be just looking for a reaction, because there's reactions there that aren't biological, and we wouldn't just be looking for replication in the sense that a fire replicates, or a cloud replicates, or a star replicates. We'd be looking for that unique biological process which we call Darwinian evolution, which involves replication with mutation and then selection from an environment. And that cycle is what has created the complexity and diversity of life on Earth. That cycle, I think, could operate on Titan. So Paul's right in the sense that there is some fundamental properties that we can ascribe to life, and we can look for them in other settings.
Now, this bit about how much energy our brain uses, that's fascinating. I think most people don't carry that knowledge with them, but that's why they always say you lose a lot of energy through your head and you wear a hat, It's related. It's a related phenomenon. Now, my afro kept my head warm completely. I've never worn a hat, and my head has never felt cold, ever.
So that might mean
They give me a hat, it's like putting a hat on top of a hat. It's just a comment. But clearly, Paul and Don, you'd be happy if you found any life at all, so we don't need to put the requirement of intelligence as high on this search for life.
No, intelligence is very low on the search.
Very low on the search, okay.
I mean, to my mind, if you take a look at life on Earth, it really is conducted by about 1,500 genes. That's it. The rest is, you know, the color of the car, the size of the windows. It's trivia. It's, you know, we worship organisms in Darwinian evolution. But in reality, all you are is like a Patek Philippe watch. You were just carrying genes to give it on to the next generation. Ultimately, every microbe...
We are what kind of watch?
You basically you're a vessel of genes. As an organism of humans, we're just going to hand off those genes like a baton to some other organism in the future. That's what every microbe is. They're a vessel of genes. And only about 1,500 of them are really, really, really important. So they're the ones that make all the life on this planet really go. You know, in effect, it's not a joke, but it's really true, that you and I are nothing but E. coli that are organized with brains and eyes and with a mouth. And that's it. We're just the same.
So we are E. coli brought to consciousness.
Yes.
Speak for yourself.
Don, what was going on in the earliest time of Earth? Because last I checked the numbers, life showed up pretty quickly on Earth.
Yeah.
If you subtract away sort of the years where Earth is still accreting from its birth sac, the surface would be hostile to complex chemistry. So subtract those years out, because that's not fair to start the clock. Wait for that to be done. Start the clock. How long did life take?
Well, in Earth history, you can see the earliest Earth's history by looking at the moon, even with the naked eye. Those huge craters. The biggest crater on the moon is on the backside. It's called the South Aitken Basin. It's almost 2,500 kilometers across. The Earth got completely creamed in its first 500 million years of history. The heavy bombardment period actually ended about 3.9 billion years ago.
And that period is called the heavy bombardment period. Just want to make that
We
clear.
call a variety of things, you know. Any organism that lives here would have called it holy, you know,
Right,
something.
right.
But anyway, so there was a period in time, which is envisioned by astrobiologists, you know, life may have formed again and again and again, but every great big impactor that came sterilized the planet. But when that was over, when the impact record ended on our neighboring moon, which records its ancient history, right after that, there's chemical and isotopic evidence that there was life on Earth. So that suggests that getting microbial life may be easy.
Really easy?
Well, who knows? We only got one. This is the challenge of astrobiology. How do we try to outsmart organisms we know nothing about? Because we only know here. We're our only data. But then it took so long.
No, but it's not just that we have no idea. If life formed almost as quickly as it possibly could have, you're allowed to say that at least nature found it easy to make life. Aren't you allowed to say that?
I think we have one important piece of evidence, that is that we have no geologic record of any part of Earth history where there was no life. That means that it's not like we had a period where there's no life and then life came. So all through the record we have presence of life. And I actually tend to disagree a little bit with you about the 3.9 billion years ago, because 3.8 billion years ago, life was already leaving a very significant imprints on the planet. And that would mean that that was not a very early type of life. So probably life 3.8 billion years ago was already pretty sophisticated in the sense that
But no records.
But there are no records of that pre-history, but it must have had a prehistory to reach a level where it could really impact the planet already.
What you're saying, it wouldn't have just been a tide tool over here.
Yeah.
Given what you see in the geologic signature.
You would have complex communities of microbes. You would have very efficient life that knew how to
already
deal
by
with
3.8 billion years ago.
Yeah.
So this happens quickly.
Yeah.
So if that's the case, and let's accept the likelihood that nature does not have trouble making life. Let's just accept that for the moment. Because I don't think that's a stretch to make that claim.
It is a stretch.
We don't know.
Yeah. I don't think it's a... It did it as soon as it could have.
We have 50,000 meteorites that were much more carbon-rich, much more nitrogen-rich, much more water-rich than our planet. They were warm and wet for a couple million years early in the history of the solar system. No life. So it can't be totally trivial. I mean, these are from asteroids.
Well, so you're comparing whether life formed on a planet versus an asteroid.
Yeah. Well, all the ingredients were there. If you were living inside that asteroid, you wouldn't know you weren't living inside.
That's true. You wouldn't know whether
you're surrounded by water. There's no sky to see. You know, it's like living in this room or something. But so there are environments.
We can make a sky
in
this facility. Just want you.
There's no life on the moon other than the astronauts that we sent there. So we do know a lot about the solar system, and we know that there's no life in the meteorites, or some people think there is, but most people don't. There's no life on the moon. The great thing about the solar system is that unlike everything else in the universe, it's close. So we can, in the coming years, go to every single place in the solar system and look for evidence of life. And even if we don't know how to define life, my guess is once we see life on Titan or Europa or whatever, we will then agree, yes, this is life. You know it when you see it.
Do your solar systems that you create on the back of an envelope and occasionally with a computer,
yes.
do they resemble, what do they look like? Can you crank out the Earths in your models? What knob do you have to turn so that either you make a lot of Earths or very few?
The surface density of solids. That's the one knob that you need to turn to get planets.
I don't know what that means. Surface density of solids.
Perhaps I should define it. If you make a star and you have a disk around it, there's about 2%, in the case of the sun, 2% of that material is in the form of things that are not hydrogen and helium, things that are not gas. We in astronomy call that heavy metals, but heavy metals includes mostly carbon and lithium, not what you think of as heavy metals.
They were heavy metals in astronomy before it was a genre of rock music.
That is
yes,
correct.
Okay.
Yes.
Just to clarify.
So not Bon Jovi, right. So the density of those solids is the single most important variable that determines whether you can make planets, whether you can make them quickly, whether you can make them in abundance in these theoretical calculations. So if you have a metal-rich system, which means that you have relatively more metals, these heavy metals, than we do in the sun, then it's actually quite easy to form planets. If you have a heavier disk, so even though you don't have relatively higher abundance of metals, but you have more gas in total, or more mass rather in total, then it's easier to form planets. So as long as you have that one variable high enough, then everything's a go.
These would be solar systems made later in the history of the galaxy, where you have much more of this enrichment to make your high surface density of solids.
Yes, well, those are the ones that are, well,
because every generation of supernovae are cranking out heavy elements, punches them into the cloud.
Yeah, no, but we don't want to be lost in vagueness here. The supernovae that cause or create the heavy elements come from massive stars, and massive stars live and die on millions of years time scale. My point is that millions of years is actually short compared to billions of years. So that you can have many generations of massive stars producing metals and still have a solar system that's quite old. The extrasolar planets that we see now, the ones around these other stars, those stars were targeted to be as much like the sun as possible, which includes the fact that those are also 4 billion years old. These are not young stars that just formed.
They're just born, right.
So even stars that old can have metals higher than those of the sun.
So maybe I'll need you in the answer to this as well when I ask this of Minsk. If in these models, if I have two identical Earths in two different star systems, they're basically identical because you can make them that way in a model. And then you just step back and let events unfold. Is there a chaotic regime in what goes on so that, in fact, they could have divergent futures?
I think that if we say, okay, they both develop life at some point in the history, I think they may start out being very identical, but they will take unique courses because today the trajectory of the evolution of life is so determined on the inventions that the life on Earth made, basically. The type of metabolic inventions that life made determined the way the planet functions today. We tend to see planet as a substrate for life, but actually life is a product, Earth is a product of the life, basically, the way it looks. You can make arguments that the continents that we live on are here due to the metabolic activities of some type of microbes billions of years back in time. And the composition of the atmosphere, we are sure, is controlled by the organisms that live here.
It's a feedback, a life feedback.
There's a life feedback. So, and probably the stability of climate on Earth is also coupled to the activity of life. So the fact that if you look back to the geologic history, it's actually very boring. You go back and you look at rocks that are 4 billion years old almost, and they look pretty much like any rock that's formed today on Hawaii.
I've always thought rocks were boring, whether or not they were old. But that's just me. I'm sorry.
No, it is true. Actually,
I'm sorry.
I will reveal this little secret. Rocks are really boring, and the Earth is an extremely boring planet. Very little happens, and even less would happen had it not been for life. Life is the only activity that's really important on the planet, and that's what processes all the energy that drives the geochemical cycles today. That is life and not Earth itself.
What happens to Earth when all our volcanoes stop? Do we look like Mars?
Eventually we will. Eventually, if we had no more CO2 coming out of the volcanoes, life and chemical precipitation would remove the CO2, the Earth would lose its greenhouse effect, and it would be, instead of plus 15 degrees centigrade average temperature, it would be minus 15 degrees.
We'd freeze Earth completely.
Just like Mars. And in a sense, this is what happened on Mars. After several 100 million years, it lost its recycling ability, its outgassing of CO2, lost its atmosphere and became cold and dry. Earth could go that way if volcanoes were stopped.
So Don, why is Earth still warm and Mars isn't?
I won't say Goldilocks, but...
No, I mean, just why as a physical body, why is it still warm? Because Mars has cooled down, right? There's no heat source inside of Mars?
For it to be born closer to the sun, we have we're 100 times more geologically active than Mars.
No, that's my question.
But we have plate tectonics, which is unique to our planet.
That's my question.
The plate tectonics is one of the big factors in keeping Earth habitable. One of the secrets...
Wait, that's not... I'm trying to understand. Mars is dead, and it has no plate tectonics. Earth has this energy source that has nothing to do with the sun that's driving plate tectonics. Why is that still happening on Earth and it has stopped happening on Mars? That's what I'm asking.
The Earth is Earth, is Mars is Mars. They already have plate tectonics.
Mass.
You have
so it's just mass.
Well,
come back over here. Mass. Fine.
It's,
No,
the
no.
answer is mass. Earth is 10 times bigger than Mars
In mass, yeah.
in mass. 10 times more mass. It's the difference between me and my cat in mass. My cat can do things that I can't do. The cat can climb up a wall. Mass, a factor of 10 in mass, changes the physical properties. Earth, being 10 times more massive than Mars, has a much more active internal heat flow and internal cycling. So the difference between Earth and Mars, I think, is not so much that Mars is further from the sun.
Yeah.
It's mass. If Earth was where Mars is, it would still be a nice place to live.
Well, then how come Venus looks so different when it has the same mass as Earth?
Well, there you're right. It's too close to the sun. Sorry.
No, but I think
It's not all mass. Size matters. I learned that on TV. But also, distance to the sun matters too.
But
okay, so it matters, distance to the sun matters between Venus and Earth, but not between Earth and Mars. So you think you can sustain an Earth as Earth at the distance to Mars?
Right. Yep. If Mars were the size of the Earth, we would be having this meeting on Mars instead of on Earth.
But it's
And if Venus were at the distance of the Earth,
it would probably be a nice place too. That's right. You got it. Now,
But if I can interject, this internal energy source must be very, very, the details must be very, very sensitive, because the amount of energy you get from this internal radioactivity is 10,000 times less than the energy you get from the sun.
Absolutely.
And
That's why it doesn't drive the chemical reaction.
Yeah.
right, so
right. But it's all
1 part in
bottled up.
10,000 makes a huge difference, right?
But there's a very important difference also, and that is that we have the ocean that keeps hydrating the ocean floor that goes back into the earth, and it basically lubricates the machinery in there. So without the reflux of water into the interior of Earth, it would also stiffen up. The Earth is soft inside. It's not molten or anything, but it's soft due to the presence of water that is being subducted with the ocean floor.
so you're saying Earth has it's like oil in a car engine.
Yeah, something like that. And like Venus has lost its water, and therefore it cannot lubricate the mantle, and therefore the mantle works in a different way than it does. It doesn't work in this steady, smooth operation as Earth does. And you can also, again, argue that the stability of the climate, the stability of the oceans, which is maintained largely by life, so you could say that the plate tectonics has been sustained on Earth for 4 billion years or more, probably also due to the management of life to some extent, or maybe to the full extent.
Paul, something interesting here.
Can I disagree with Minnick for a second?
No.
Sure. Wait, what about it are you disagreeing with?
Well, life is really important for disequilibrium of redox reactions. It takes and makes gases because it moves electrons around. But
What you're saying is inside a physical organism, we are highly out of equilibrium.
right, exactly.
Okay.
But you would have a carbon cycle on this planet without
Sure.
life,
Yeah,
and we
sure.
have 3 or 4 oceans of water in the mantle below the ocean that we physically see, and that would be there without life also. So I think we over-ascribe this Gaia-esque world to, at least you are, I think.
But just briefly, Gaia-esque, just tell everyone what Gaia is.
Well, Jim Lovelock hypothesized this kind of feedback that life and the planet co-evolve, so that the planet's surface conditions is always made possible for the future of life by life itself. There's a feature of life that makes life more conducive for life.
So life is a stabilizing factor in the dynamics of the planet.
And as our mutual friend Joe Kirschmink at Caltech would say, well, if that was true, then we wouldn't have had snowball Earths. Snowball Earths were a period in time, starting at around 2.2 billion years ago, shortly after we oxidized the atmosphere, where all the oceans appear to have frozen. And they froze for maybe about 100 or 150 million years. We still have refugia somehow for life. But certainly, we stopped basically the hydrological cycle. The surface planet became very cold. And this happened apparently 4 times up until we got the Cambrian explosion.
But that notion got a lot of play.
It did.
It did.
Yes.
More than perhaps it deserved.
I'm not sure. I think it's a very interesting thing of how can you get a planet so far out of its thermal zone, comfort zone.
So that it never comes back.
It never comes back.
Well, it doesn't never come back. It
In
came
this-
back.
It came back because of tectonics.
It came back because of volcanism
Right.
persisting, driven by tectonics. So as long as volcanoes are a good thing, they'll knock the snowball Earth eventually.
Okay, so what day will we lose our volcanoes?
We've got several billion years worth of radioactivity left in the interior.
And we also have the liquid core that's producing a lot of heat when it's solidifying. So we have two heat engines actually, not only the radioactivity, but we also have the liquid core, which is releasing energy as it crystallizes.
And we still have heat left over from our formation.
Yeah, that's in the liquid core, exactly. Yeah.
Okay, so we have heat from our formation. You got heat from all this movement. I guess it's friction down there. You had heat from radioactivity.
Right.
And you just said a moment ago, which I hadn't heard this number, that it's what % of the total sort of energy budget of the Earth when you add in sunlight?
Well, it's
1 part 10 to the 4.
10 to the 4th.
One in 10,000.
Yeah.
But that's misleading,
Yeah.
because most of that sunlight comes and hits the Earth and leaves, whereas this geothermal heat is coming from deep below the surface of the Earth, and it's driving the volcanoes and the tectonic
It's actually
activity.
getting busy.
It's doing something that sunlight isn't doing. So
Well, in fact, it has to do something in order to get out, right? That's what it
It's
does.
heat trying to get out.
yeah,
No,
yeah.
yeah, because it
When
has to
Chris, when I
propagate
park
through
my
the rock
car
layers
in
to
the
do that.
Mojave Desert at night, it's got 4 tires touching the ground, and yet it's radiatively more related to space than it is to the ground. It's not
Right.
getting heat through the tires
Right.
to keep it warm,
Right.
okay?
Right.
It's getting heat from the sun during the day, and it's radiating it back at night.
Right.
And that's what most of the planetary surface is doing.
Surface, right. But the subsurface is what drives the volcanoes, and that subsurface.
But the surface is where the light energy is transforming molecules to make chemical bonds of life. And one more thing. You know, to me, discussing the origins of life as being simple or not is like saying you can talk about the theory of jazz, and one day somebody like Thelonious Monk comes along and plays something. Okay, so nature really.
No, I didn't make that. I didn't get that connection.
Nature was somewhere along the line of Thelonious Monk. It wasn't just a theoretician of learning jazz theory. It learned to play the piano, and it took molecules and it made stuff. And it made stuff that replicated, and it made bugs. And we can't do that. We haven't been able to do that yet. So even the very simple redox reactions, like water splitting, we don't know how to do. We don't know how to make nitrogen into ammonium at room temperature. And
But why should what we know how to do be any measure of what was possible in the early universe?
Because we know the structures of those molecules at very high resolution. And when we talk about astrophysical space that is phenomenal in terms of what a telescope can see. Well, conversely or obversely, we have incredible resolution of molecules. And we can go down to 1.1, 1.2 angstroms and see how these molecules are structured. And yet we can't replicate them. If I were to change the world for our energy budget, I would invent a catalyst that splits water. And if I could split water, I'd get hydrogen. The world changes instantly. Instantly. So we have then an infinite source of energy for the rest of human civilization.
Well, so this brings up an interesting point. A pretty important chemical reaction in the early Earth is photosynthesis.
Absolutely.
Okay, it's nature figuring out a way to exploit the energy from the sun.
To make new bonds.
Because why not?
Right.
It's available to you. That reaction is interesting. I remember learning about it in biology, but it wasn't so complex that I couldn't imagine it happening naturally. Would that be something that you think might be inevitable on any planetary surface?
You know, it's still a Darwinian eyeball. It's one of those things that occurs on Earth, and yet we really don't understand how this thing came to be. So it occurs. I think every biologist that studies the reaction believes in the evolution of this through some natural selection process, but we still don't know the very early blocks that allowed the electrons to be moved because of photons.
Why not?
Well,
I got Fred Adams over here claiming he knows how planets were born. You can't figure out a molecule for early...
Yeah, the trick of photosynthesis is the back reaction. So if I take an electron off of a metal like manganese, which is where the original electron comes from before it oxidizes the water, and I put the electron somewhere, in most cases, it just goes back down, and nothing happens. So the magic of the photosynthetic reaction is to move the electron, and then we put it someplace where we stored it, so it doesn't go backwards. And that's been very, very, very hard to do for humans to mimic that. We almost can do it. In the next 20 years, we probably will be able to do that pretty well. But it's been one of those...
Maybe biology is just still kind of in its infancy. I know it's hard to admit that as a biologist, but...
No, not at all.
Okay, so maybe it's in its infancy, and you need another century of this effort before you can show that something that today is viewed as complex in 100 years would be viewed as simple. We've been through this in physics.
Exactly.
We looked up at the night sky, planets were going through retrograde, nobody understood it. Newton comes along and writes down the equation of gravity. It is trivial, you can do it on your iPod today.
Well, exactly, the analogy is exactly right. The beginning of the last century was the beginning of quantum mechanics and the understanding of physical properties, and the physicists ruled the 20th century in science. I think this is the century of biology, and biologists won't rule in the sense, but they'll understand the rules of biology, which has been a very, very difficult thing to do.
So, all right, so...
Well, physics isn't quite done yet in the sense that...
Still things to do.
No, but I actually wanted to make an analogy, not a joke. One of the things that...
Wait, just quick. This is that wormy thing that was on the Mars rock, Allen Hills 8401. And we don't know if it's really a worm. It was just intriguing. The photo was published alongside the research paper that described it. So I don't know. It was a quick... These are just random wallpaper about life on Earth and elsewhere. So I interrupted,
I
sorry.
was just going to make the point that just because we can't reproduce something in the lab doesn't mean that nature can't do it readily. A good example
Or
of
easily.
A good example of that is something called fusion. Every star in the universe runs on nuclear fusion. In our physics labs, we've been we found it remarkably difficult to produce a sustained...
Inept.
Yeah, that's a good word, inept. To produce a sustained controlled, keyword controlled fusion reaction. It's really easy to build a bomb that is an uncontrolled fusion reaction, but it turns out to be really, really hard to have a controlled fusion reaction. But that doesn't mean that nature has any trouble with it. Nature does it billions and millions of times in billions and millions of galaxies. So
let me ask, in the planets that we're now adding to our inventory of the exoplanets, we have who here can tell us about the Kepler mission? Who's the best among you to just brief us on that?
I can tell you.
Go ahead. Just tell the Kepler mission.
Well, just to lay the groundwork before the Kepler mission, using ground-based astronomy, we now have a database of approximately 400, 450 planets discovered one at a time by telescopes. The Kepler mission is a satellite that's measuring the presence of planets in a different way. There's there's 4 different ways to measure planets, but the 2 that have found the most fruit are what's called the radial velocity method, where you watch the star wobble back and forth in the sky, and then you deduce...
In reaction to the gravity of
In reaction to the gravity of the planet, and from that signature you can deduce the properties of the planetary orbit, the mass of the planet, and so on. The other way to see planets is if you have a star and a planet goes in front of it, then the planet will cast a shadow on the star, and the star will appear dimmer for a little bit, and then the planet will pass the star, and the brightness of the star will shoot back up. That's called a transit. So the Kepler satellite measures transits. And it published a paper in June where it gave partial discovery claimed partial discovery to 400 planets. Now the full story is that there are 800 planet candidates, and of those they decided that 400 of them were interesting and they didn't want to release to the public, so they're keeping them in their drawers, as in their desk drawers. So that we can't see them yet. And then the 400 of them that they deemed less than interesting, they published as in, these are the planets, these are the stars, these are their properties. But what's confusing about that is that they haven't figured out their false alarm rate correctly. So they've thrown out everything they know is a false alarm, but they still figure that of the planet candidates they have, about 1/4 of them are actually not really planets. So we have another 400 planets discovered as of June, although only 300 of them are real, and what's a little bit frustrating is that we're not sure which 300 are the real ones.
Right, but the takeaway here is that
the takeaway is that there will be hundreds of planets.
It's a mission tuned for finding Earth-like planets.
Yes, and we're finding many smaller planets in this sample of 400 potential planets than we have in the sample of radial velocity planets.
Because that one required the more massive planets
it's
to
easier
tug
to see
the
big
host
planets
star.
because they wiggle their stars more.
Right. So we're gonna go to questions from the floor. We have 2 microphones set up. We'll go into just a couple of minutes, but just think about your question and feel free to come up. I just want to go down the line here, and I don't know that we resolved anything, but let me just get your take. Yes or no? So is Earth unique in whatever what the word unique means to you? Is Earth unique?
I think it's unique, yes.
You think it's unique? What do you think? Of course you say yes. Okay. Paul.
I go with the odds. It's not unique. I think that
Not unique.
when you have 10 to the 11th stars in the Milky Way in our galaxy, you have a 10 to the 24th or some number like that in the universe. I think the odds of it being unique are incredibly low. I mean, you just do the numbers for the Drake equation. You just need the front end.
Well, let me ask you this: is it not unique in a neighborhood in our little zone, or do you have to really cross the galaxy to find one?
I would hope that.
So how unique is it?
Well, how unique is it? What if we're looking for life?
How pregnant are you? You know, how unique is it?
I think the question, the seminal question is this the only planet in the universe, for example?
A good shot of Earth here now.
That supports life. And if I view life as something that is far from thermodynamic equilibrium, that can self-replicate, then it leaves a gas trace somewhere. It should leave a gas trace. And therefore, long before there was oxygen on this planet, there was probably methane and nitrous oxide that coexisted. We could have seen in that universe at that time, if we were sitting with an interferometer, for example, evidence of life on this planet, even though humans were not here
The
yet.
gaseous effluences of life
Right.
thriving
I
on
mean,
its surface.
We're basically looking for reruns of Gilligan's Island from, that's what what Search for Intelligent Life is doing, looking for reruns of Gilligan's Island from some planet 20, 30, 50 parsecs away. I'm not sure that we'll ever find that, but I certainly think that we'll find disequilibrium gases. And if you see methane and nitrous oxide on a planet 6 parsecs away, game's over.
Well, Gilligan's Island was a TV show in disequilibrium, right? That's right. Let us hope that that's not our cultural emissary that is first discovered by. Unique or not?
Life is common in the universe, so in that sense, Earth is not unique.
Wait. You think life is common in the universe.
Right.
You didn't say that. You just said life is common.
Right, I think.
Yes, sir.
I'm not from Roswell, New Mexico. I have no inside information to share.
He is not authorized to divulge. Fred, what do you got?
Well, I would say that Earth-like planets are common. So to be more specific, if you just ask the question about the planetary properties, rocky bodies are easy to make. We see lots of them already. We're about to see one as small as Earth any day now, literally, in the astronomical observations. And it's only a matter of time before we find some in the habitable zone. There might have been one discovered in the habitable zone a couple of weeks ago, the one that you talked about in your introduction. So the planetary properties, the beds for forming life, if that's what you consider an Earth-like planet, were there already. The next question is there life on them? Well, I agree with the last two colleagues here that life is just a physical process. Physical processes happen everywhere.
Life is just complex chemistry.
And
at some level.
It would be remarkable if it were not at least life in some form common. I mean, everything else that we've seen in astronomy, we found black holes that have millions of solar masses. Well, they're not unique. There's one in every galaxy. We found neutron stars that are something like taking the whole mass of the sun, putting it into an 8-kilometer sized thing and spinning it 1,000 times a second. Well, there's millions of those in every galaxy, and there's billions of those galaxies. So, it would
by the way,
really
this creates a fundamental philosophical rift between the astrophysicist and the biologist, because we get stumped practically weekly with cosmic phenomena that we never ordered.
And then we get millions and billions. So from that point of view, or coming from that point of view, I would have to place my bets, and I'm only placing bets, that life is common.
Don, I swung by you pretty quickly, so let me give you a chance to speak. So life unique or not?
Well, the real question is how abundant is life? I mean, on our rare earth hypothesis, we suggested what I think most people believe, that microbial life is pretty common. But animals, how abundant are they? And it doesn't matter that there may be 10 to the 22 stars. We will never know anything about that. We still don't know whether there's life on Mars, even though it's really in our backyard. The real question is, of the nearest couple hundred or 1,000 stars, is there something like us on them that we can detect with telescopes in the next century or time scale? So it doesn't make any difference if it's in another galaxy or the other side of our galaxy. Is it nearby that we can ever detect it with techniques from Earth? And the other question is, can we ever go there, or will they come up?
Well, I go with Paul, because like he said, if life is a vessel that's out of chemical equilibrium, otherwise it couldn't really survive. If you're in equilibrium with your environment, the other word we have for that is dead, okay? That's what... I'm not exaggerating, right? When you are in equilibrium with your environment, you are the same temperature as your environment. You are just simply dead. So I agree that there would be a biomarker in the atmosphere of these planets. So perhaps, while we'll never visit them in any foreseeable technology we have lined up, a carefully designed optical experiment, spectra of the atmosphere, we can find chemistry that we know is out of equilibrium.
Right.
That would tell you that there's disequilibrium chemistry going on the surface, and the best version of that we know of is life.
Exactly.
This is a
Well,
tremendous...
I just say that this unique business is, I mean, is at what level are we discussing? It's like, are you unique, or there's 6 billion people on the planet, so you can say humans are common, but you're still unique. And I think it's the same level that I think that Earth is unique, is that biology in its evolution is not deterministic. It's not meant to end with us, or not end yet, but it might end with us.
The roaches are waiting to take over after we kill ourselves.
So anyway,
they're going to have museums with humans.
So I think that
like we have dinosaurs.
But life is probably very common. I agree with that, but I think that the chance that life would develop into us is extremely unlikely, and by that measure, I think that our Earth is unique in having exactly the makeup that we have.
I think
here.
there's a confusion here, though.
Yeah.
So what we're talking about is metabolic processes that seem to be common versus the life forms that seem to be unique. Okay, so evolution is not predictable in the sense that we can't determine the outcome of evolution.
Yeah, we're not asking here, is there another planet with dinosaurs that went extinct with an asteroid and mammals rose to become... That's not what we're talking about here.
Exactly.
Just a system that supports a thriving biota.
Right,
Then
and
we're
there are
common.
limited
Oh, then
combinations.
Yeah,
so you change your view.
absolutely.
After 4 other people had disagreed with you, you
No,
just
no, no,
backpedaled here. I just want you to know. That's what it looked like. Okay. Between you and me, it's okay. We'll tell you. Let's take a first question from the floor here.
I'd like to thank the panel and Dr. Tyson for tonight's debate. According to the app, 492 exoplanets.
He's got the app! He's got the app. So the number's 492?
492.
So we should have a 500 party. That'll be in an hour and a half.
My question goes to the engineering of actually determining the answer to this question. Given today's technology, how far away would what is the farthest you think we could be from Earth in order to determine, using our technology, if there were life on Earth?
That's an excellent question. Let me go to you. Did everyone get the question? No. So the question is, here we are on Earth, and we know there's life, and we're trying to determine if there's life on a distant planet. How far would we have to step away from Earth before our current technologies would not be able to see that there was life here as we know it? That's a good question. That's a reality check on what hopes we have of finding Earth on a distant planet. So
the most obvious signature of life on Earth is the oxygen in the atmosphere and the ozone that's produced from it. So the question, I would rephrase your question as, how far away from Earth could we still detect the oxygen, the fact that the Earth has an oxygen-rich atmosphere, using telescopes like we're developing now? And I think the answer is it's going to be pretty far away. I would guess.
Can you be a little more quantitative than that, please?
Guess.
We got scientists here. It's just pretty far. Yeah. Oh, that's how far away.
Yeah. I would guess as far away as this planet, at least 20 parsecs. I'd say
20 light years. 20 light years.
20 light years.
Yeah.
No, more than that.
Easily 20 light years.
GI 581G is 20 light years away.
Is that not what I just said?
It's also
I thought I just
extremely
said that,
close to
didn't
its planet. You'll never resolve it.
But
I got a microphone. I just said
If there
that.
was an Earth-like planet.
No. We were getting the
star,
distance to that star
Okay.
at 20 parsecs, but you're thinking we'd discover it much farther away than that.
No.
20,
Yeah.
20 light years.
You just have to stare at it. The photons coming from the object, if you can stare at it long enough, it's just time.
In fact, if you get
what would
starlight
you do
behind
right
it, you
now?
catch it in absorption, and you have a much more sensitive detection. Okay, so you're thinking about that distance, you're thinking.
With telescopes we have now, which, for example, Gliese was not detected by direct imaging. It was detected by, as Fred said, by velocity
The Doppler
change
shift.
of the star, right? So it's not obvious that we can map out the composition of those worlds even that close, 20 light years. So I think 20 light years would be a challenge with current technology. And we can imagine interferometers in space and chronographs in space that can do much better and could separate the planet from the star. We don't have those in orbit right now.
Nor will they be in the next 10 years.
Right,
So I just
because
served on a decadal survey
Right.
panel.
They're not in the cards, but we know how to do them. So if the question was, how far could we see an Earth-like planet, say, with the technology that we can imagine now and build in the next 20 years in your professional lifetime, then I think the answer could be many, many times farther than that 20 light years. And again, oxygen is the obvious fingerprint of life on Earth. If you think of the Earth before the rise of oxygen, as Don said, there was a long period of time when Earth had life but no oxygen. Then the fingerprints are much, much more subtle, and I don't see any prospect of detecting them more than a couple light years, even if we can even do that.
Excellent. Okay, next question right here.
Okay, this may be for Chris McKay also.
Oops.
How long will it be before we get rocks and material back from Mars to tell if there was life there? And do we have to send people to do that, or will rovers and other things be able to do that?
Did everyone catch that question? Yeah, so question is, do we go bring rocks back and study it here to be sure whether or not there was life, or do we send astronauts there? What's the plan for this going forward?
How long?
How long?
How long? The Academy, the National Academy, will request that NASA bring back samples within the next 10 years. That'll be part of the decadal survey. Will we be able to do it? Mars sample return is kind of like fusion. It's something that's always out there. We always want to do it, and we always think that in 10 years we're going to do it. And 10 years comes, and we think, okay, another 10 years, and we're going to do it.
But it's a little different in that the fusion has some real there's instabilities and technological things we don't understand. We could probably do the Mars thing if we threw enough money at it. The question is,
good point.
Do we have the budget for it?
That's a cultural barrier, not a technological barrier.
There are some technological issues as well. But,
but the answer is the same.
He's right. That's why I shut up. Right here. Go ahead.
Okay, this one's for Fred Adams. Now that we found the Goldilocks planet, what's the probability if you crank different parameters of the solar system to have that found? What's the statistical idea of finding on the various different kinds of solar systems that are possible something with that kind of a configuration?
Well, the honest answer is that we don't have enough data to...
But just so I understand the question, are you asking, now that we have one in the data set, can we assign a probability to the frequency of those among star systems?
Depending on which way, depending on how you form a star system.
Okay.
Well, we can't answer quite the question you would like because we simply don't know. We don't have enough data. I mean, what we do know is that we've discovered, almost 500 planets. And of those
492, we already know.
492.
Thank you.
As of
you can be precise
ago.
When you can. We got it. The man told you.
That's exactly right. And of those 492, one is close to habitable, if not habitable. So you would naively think that there's kind of a 1 in 500 odds. What you need to realize is that when you have one event, the error bars on the odds are 100%. So I wouldn't want to give you any odds because they would basically have infinite.
Small number statistics is the problem.
Yes, what we would just sum it up by saying it's small number statistics. Yeah. So we desperately need more data to answer your question. So we'll get that in the next, I would say, 5 years, and then I'll have something more intelligent to say.
So at that point,
not that you haven't been intelligent thus far.
Well, I've been trying.
Right. Okay.
Okay. So then you could project that based on certain stars, that these stars would generate a certain number of different kinds of planetary systems, and therefore 1 out of maybe 1,000 might have a combination of factors that would give you that kind of a planetary system.
Right. If we have enough data, we could start to answer those questions. What we now have enough data to say is that something like 1 in 5 to 1 in 4 to 1 in 3 stars we expect will have planets of some kind. And then some fraction of those will have what we call Earth-like planets, but we don't have good enough statistics on the
Kepler should bring in enough planets to really make good tabular statistics on this.
Yeah. It's supposed to. That's exactly why we funded it. We just have to wait only maybe a year or two, and we'll know a whole lot more.
Wait, who's the we here? You said we funded it. You write equations on the back of an envelope. You didn't fund a thing. What?
I mean, we, the country.
The country. Good.
It's called taxpayers.
So Gliese 581G is in the habitable zone. No one knows it's habitable. We don't know that it has an atmosphere, that has an ocean, it's a very different world. If all the solar systems are like ours, and the planets are logarithmically spaced, each one about 70% further, we expect that typical stars would have a couple planets in the habitable zone. So don't call these habitable just because they're in the habitable zone. It means they have a chance of being habitable. They also need atmospheres.
But that's just semantic. No, some irresponsible journalists said that it was inhabited, but most of them got it right. That it's
that was a scientist that said that, not a journalist.
Oh,
never mind. Never mind.
Or was it actually a correct quote of a misspoken statement from an actual scientist?
The key word they said that I believe, and that's a very important thing in this whole field, is belief. A lot of this comes down, do you believe X, Y, and
Are you saying one of our colleagues said that he believes Gliese 581G has life?
100% chance of life.
Who said? Who?
I don't know. I forgot.
First author on the paper.
Oh, is that right? We'll have to straighten him out.
Yeah.
Yeah, you don't, as a scientist, you never want to overstate.
100%, maybe 99, but not 100.
You don't want to overstate what your data allow you to say. Otherwise, you compromise your integrity forevermore.
One other way that the Earth is unique that no one's addressed, and this is to the panel, is that in terms of the ratio of a primary to its satellite, the Earth to the Moon, and the effect that the Moon's formation had...
The ratio of the sizes.
Right,
yes.
Right. It's, the ratio of the sizes. And the effect that the Moon has had on the Earth over the, over the billions of years, for example, its formation caused the Earth to be tilted, and we now have seasons because of that. It created the tides, which churned up the basic oceans. It slowed the Earth's rotation down from 8 hours to 24 hours, which means we don't have 200-mile-an-hour prevailing winds. I mean, no one has addressed that, and that, I'm not sure about Gliese, but does it also have a large satellite to do those same things that would allow the Earth this other Earth to evolve?
Don, I want you to handle that. So how important is the Moon to everything we just discussed?
Well, I think, you mean Don or me?
Oh, so I call you Don? Sorry, Fred, sorry. Uh-huh.
Well, I think Don actually knows the answer to that more than I do. But
well,
Don, how important is the Moon here?
The Moon is important, but it's probably not a killer. If we didn't have a Moon, we could probably surely still have life on Earth, but it would be different. I mean, one of the secrets of Earth has been stable for billions of years. Mars hasn't been stable. Venus hasn't been stable. One of the factors that kept
Wait, Venus is stable at 900 degrees.
Venus,
just because you don't like it doesn't mean it's not stable.
Venus lost all of its old history. The oldest things on the surface of Venus are only about 900 million years. It completely turned itself inside out.
Okay.
It's a really...
It repaved itself.
Not only is it Halley's hot place, it turns its lid over it. But so the Moon has helped keep the Earth's spin axis fairly constant, so we don't melt the poles and cause all kinds of catastrophes.
We just have a different set of configurations and maybe a different trajectory that life would have taken.
Yeah.
But you don't think it is a deal breaker?
Well, it's not. It would be a deal breaker for us if the Earth started spinning at 40 degrees instead of 22 degrees.
Well, that's good. In 2012, that's what's going to happen. Right? That's what we hear. I'm not authorized. No. so I didn't know that myself. I mean, what measure of importance that would have been, because just to clarify, the Moon's size relative to Earth is largest of all the planets.
The planet Pluto also has a large moon.
Yay for Pluto!
The dirty ice ball in the outer solar system has a large moon. Yes.
You'll never live it down. You'll never live it down.
Right here, yes.
Yeah, hi. Just a quick comment about finding life on Mars. I think the reason we don't know whether there is or was life on Mars is because we don't want to badly enough as a society. The technology is there. We could send more robots. We could send people if we really wanted to. But we haven't done it because we don't want to badly enough. But that's actually not my question, sorry. The question is...
That's good, because it actually wasn't a question. Yeah.
It wasn't. Okay. It's true. That was an editorial. But the question is, I think everyone would be really thrilled if we found microscopic life someplace, but doesn't everybody really want the next Asimov debate to have somebody from Arcturus come in? What's the probability of having multicellular life, much less intelligent technological life? Or can that even be estimated?
You want me to invite a microbe as my next guest on... No, I missed the thrust of the question.
Can can you make any estimate of, most people are saying there's probably life,
Yes.
but we're talking about microbes.
Yes.
Is there any way to make an estimate of what's the probability of multicellular life and ultimately technological life?
What was the selection pressure for multicellular life?
You're supposed to answer the question.
Yes, yes, she's. You're the man.
The answer is I don't know.
Okay, so we don't know really, but we think it's because we ran out of certain nutrients and foraging behaviors and behavior in general became more efficient. So if I were to take, at some point you are an energy dissipating organism, as Neil said. You're not in equilibrium.
I used easier words than that, yeah.
But if I were to take...
Energy dissipating organism, though, did not come out of my mouth. Okay.
If I were to take you or Neil or myself and dissolve us into our single cells, our individual cells, and put them out onto a petri dish, our individual cells would have a metabolism about 1,000 times greater than we have as an organism. So multicellularity came about as an energy conservation system. In places where you have lots and lots of energy, there's no selection pressure to ever have multicellularity. And this is one of those things that I don't think any biologist really understands why we developed this process, why nature created multicellular organisms to begin with. They don't diffuse materials very well. They're usually limited. You're limited by oxygen right now. Well, you may not realize it, so am I. We have major problems. Our reproductive rates are much lower. It's much better to be a microbe and stay that way for a long time, which is why they persist.
I don't want to be in somebody's digestive system. I'm sorry. I'm staying as human.
Multicellularity is not a necessary thing for life.
That's a fascinating point about the efficiency of energy. I didn't know that. Thanks. Next question here.
Yes, pertaining to
Well, I have to say, this is the creator of the contest-winning video for the Rose Center. Turn around and wave to everybody.
Very humble.
We flew him in from Los Angeles, and he's here for the weekend with family. So thanks for coming to this. And for your, his video was on the Large Hadron Collider. It was hilarious, it's fun, it's accurate, and he was inspired by that as well as other science topics, but that one in particular brought him to create a video on it. So now that's your big preamble. So your question better really be good after this.
I'll do my best. Pertaining to the Kepler mission, I wanted to know what factors led to the decision for what patch of the sky that we pointed the telescope. Because, correct me if I'm wrong, but it's only a small area of the sky that it's pointing?
Yeah, who can take that?
I think you'd have to ask the Kepler team for details. I mean, it's always an optimization problem of, do you look at a part of the sky and do you look deeper, or do you look at more of the sky and you look,
Is Kepler at L2 on the other side of the moon?
I actually don't remember.
No, it's a drift-away orbit from Earth.
It's a what?
It's a 30-inch telescope, and it looks at 200,000 stars.
Right.
And so it can't look at the whole sky. It's a miracle what it does.
No, it's science. But go on.
No. It has to measure the brightness changes of 10 parts per million, and they proved that they could do this by drilling little holes in a plate and putting little wires in front, shining a light through it, and heating the wires up by running a little current through it and made it swell and block out the light. People originally didn't believe that you could do this with existing technology to this incredible precision. It's an orders of magnitude higher than ever been done before in measuring star brightness. So it is a miracle. Technological miracle.
And so maybe the point here is, whatever is its field of view, 200,000 stars are getting monitored. And keep in mind, you have to continue to watch them because you're looking at the light dim and come back up again. It's not just snapshots. Typically in survey telescopes, you take snapshots, you move the telescope, take another shot to get it. Here you have to keep at the stars to build your data set. So we don't have the luxury of doing that for the whole sky, but 200,000 stars, that still feels pretty good. And that'll all be coming over in the next couple of years once they get their understanding of their uncertainties hammered out. Yes, next question.
This is a kind of, it's a more simpler question to the other ones that have been asked, but if another Earth was discovered and it had a special uniqueness compared to this one, could we survive without the magnetic field?
We haven't talked about magnetic field.
How important is the magnetic field? Mars doesn't have one, right? Mars does not have a magnetic field. And a lot of people ask me about that. How could life on Mars survive without a magnetic field? Well, Earth occasionally loses its magnetic field. We can look back in Earth history and see times when our magnetic field flipped from north pointing to south pointing, and during the time in between, there would be no dipole field. And those times in Earth history do not line up with extinctions. So I conclude from that that a magnetic field is not essential for life. And why you say, well, doesn't the magnetic field shield us from radiation? And it's certainly true that a magnetic field steers solar radiation toward the poles where it forms beautiful aurora. But even without the magnetic field, that radiation would be stopped by the thick atmosphere. So I think a magnetic field is nice. It's good for compasses. It's good for aurora.
Compass? You still use a compass?
Yeah.
I'll get you a GPS thing after the show.
Merit badge.
Yeah, okay.
Merit badge. But it's not, without a magnetic field, life is still possible. Complex life is still possible. And intelligent life is still possible.
So people have been made too much of the magnetic field, I would say, then, over the years.
Yeah, to be clear, the radiation that Chris is talking about is what we call cosmic rays. So these are particles, charged particles, not photon radiation.
Yes, thanks for that clarification.
And the other thing,
solar flares,
and that are caused by solar flares, yes. But you could argue it the other way if you wanted to, even though we don't know. And that is that the cosmic rays might cause mutations, which could lead to extinctions, but they also just might cause evolution to work better. We don't know.
There's also a worry that a lot of people have that if a planet doesn't have a magnetic field, when the star is young, they're much more active, energetically active, with all these particles coming out, which strip off the atmosphere. I mean, that may be one of the reasons that Mars has such a measly atmosphere.
Wait, but isn't it true that half the biomass of the Earth may be beneath the surface? So what goes on the surface might just be irrelevant to most of what's going on?
No, I agree that life could easily be shielded from the radiation, but I think the big question is, could we potentially lose the atmosphere by abrasion from the strong radiation that is otherwise deflected around the planet? So
what you're saying is the high energy can actually ablate the atmosphere off the planet.
Yeah.
That would be a bad situation.
Venus also has no Venus has no magnetic field, and it has an atmosphere. So this is what is taught about, and we're taught what the big deal is to keep an atmosphere is size.
It doesn't have a nice atmosphere. No, but a bad atmosphere.
But if you're a big planet, you can keep an atmosphere much better than if you're a little.
Depends on lots of complicated factors. Magnetism is good.
We've got.
I say down with magnetism.
We're going to go 5 more minutes, and then we'll break. By the way, I've convinced the panel to hang out afterwards. We're going to go into the Hall of Northwest Coast Indians, and while several of them have actually written books, none of them are here, but there are other books on Earth and the cosmos that you can buy. And what people like to do is sometimes get them to sign your program. So we'll be hanging out in the corridor if we don't get to each one of your questions. But I just want to have a definite ending time here. We'll go another 5 minutes. Go. And try to be quick so that we can get as many going on in 5 minutes as possible.
Yes, sir. Dr. Paul, I hail from New Orleans, Louisiana. And I have to defend my state and the people of Louisiana, that there are plenty of intelligent people in Louisiana. If only the Corps of Engineers would listen to us.
Oh, there you
go! He would. So we definitely don't want any Tony Hayward-esque type of mentality that we love New Yorkers have towards Louisianans, please.
Mm-hmm.
And Dr. Tyson, you may be confusing with the guns of Texas, not of Louisiana. So regarding, be sensitive. Y'all got Whit Marcellus, so, we love y'all. I was just I guess it's more of a statement as well, that I deal in the area of science, but just on another level with medicine. And I love the banter back and forth. But I think that as long as what's important for science in all fields is that as long as we keep open and that we don't kind of close things off, because 50 years ago, we would never thought about marine life with bioluminescence or living near those vent stacks, down in the basins of the oceans, or heart transplants.
So the most successful scientists are the ones that do have that open mind.
Absolutely, yep. And who are willing to listen and not be so, so set in one path, but, just kind of I think that's where a lot of the growth happens.
Well, that's why we try to get the bleeding edge of
Absolutely.
on the
so
stage.
Like, exactly, and you clarified it when you said like what is unique, and that's one of my things is, well, what is unique? I mean, define unique. It may be different because we may have another system looking at us discussing the same thing, but to them, what we do is totally, off the charts.
Out of their box, across the street, as we
Absolutely.
learned earlier.
Okay.
Thanks for your comments.
You.
Thanks. And thanks for coming up from Louisiana. Okay, next question, sir.
Putting aside the idea of methane-based life and oxygen probably being the most possibility, plug for this museum, which has the red banded iron. I work, by the way, in the Hall of Planet Earth. And
you're a Hall explainer there?
I am the Hall of Planet Earth.
Okay.
And I work it. And the idea that biological affect is what's going to keep the planet going. That is, as you probably know, the red banded Earth hypothesizes that stromatolites, a kind of algae, developed oxygen, which then gave our planet a 20% oxygen ratio.
Well, these are the life forms you were referring to that were very far at the beginning.
So the point is that our life forms really needed for self-replication. I mean, that sounds tendentious, but are they needed for self-replication?
Are life forms needed for self-replication?
Are the algae necessary, the oxygen that they produce necessary for our replication? We wouldn't be here. The oxygen, we have O3, that, by the way, would stop the...
So what you're saying is we went through this whole period of time in the history of Earth, no oxygen in the atmosphere. The algae is making, I guess the cyanobacteria, whichever it is cranking out the oxygen. And so what I wonder is if you were sucking away the oxygen while that was happening, would we keep that bacteria there and we would have never arisen? And that emergence of oxygen, then is that what enabled the complexity of life?
It enabled the evolution, we think, of animal life. So without oxygen, we would not have animal life. All animals require a metabolism that is based on oxygen. But to get to the point, there was probably between a 600 or maybe even an 800 million year lag between the evolution of cyanobacteria and the stromatolites, the guys that make the oxygen, and the actual oxidation of the planet. And that period, I mean, it's without tectonics, again, if we didn't bury the carbon, we would not have any oxygen on the planet. So it's not a simple thing. Just because you make a bug that splits water and generates oxygen doesn't mean you have any oxygen on the planet. Right now, we're breathing oxygen, plants are making oxygen, the oxygen concentration of the planet doesn't change. It hasn't changed substantially for hundreds of millions of years. It's in balance. There was one tipping point at about 2.3 or so billion years ago, we think, where they went from a world without oxygen to a world with oxygen, and we never went back again. And understanding that period of Earth's history now is really one of the more exciting areas of geochemistry.
And just to clarify, when you said it's in balance, there are two kinds of balance. One is a ball at the top of a hill, carefully placed. Another one is the ball at the bottom of the hill.
Right.
They're both in balance, but one is stable, because you displace it one direction, it goes back.
Right.
The other one is unstable. You displace it, it rolls away. Right. So you're referring to a stable kind of equilibrium here.
Right.
Yeah. Okay, thank you, sir. Got just a couple more questions here. Yes?
Hi. First, I just wanted to thank the panel for a fascinating talk. I teach high school in New Jersey, and I'm looking forward to telling my students about all of this. My question is actually that somewhere early in the talk, I think it was our moderator, who was making an argument and said essentially, well, you're just talking about processes that we already know. Why can't there be some processes that we just don't know anything about?
That was it.
What I want to know is, qualitatively, how is that different from the people who say, oh, well, we thought we couldn't break the sound barrier, and we did that, so why is light speed a limit, which is an argument that generally is pretty well rejected. Why is that argument any more valid than the light speed argument?
Well, okay, I can tell you that the sound speed, those were just really ignorant people saying you'll never break the sound barrier, because at the time they made those statements, rifle bullets went faster than sound. The whip at the tip at the end of a bullwhip goes faster than sound. That's the crack of the whip. So to say we will never go faster than sound, they're making a technologically limiting statement, not a statement about the limits of nature. To say we don't go faster than light, that is not a technological statement. It's a statement of the laws of physics. So you make an interesting point is that do we know biology well enough to assert that we know the limits of how you would have biology on another planet? And is that the same kind of statement as when we say there's the limit to the speed of light?
No, I think we know if we base life on extracting energy from some substrate, like a sun, or from methane in the case of Titan, for example, then there has to be something that, if we're going to oxidize methane, you can't reduce methane. Methane is reduced as far as it will go. You're going to oxidize it, which is the reaction that a life form would search for. Then what is going to be the electron acceptor? What are going to be the products? And that is really where I'm going from. We can think about this in a very, very logical way. There are organisms on this Earth that oxidize methane. They produce CO2 as a result of that. And so we should see in a planet that has life, for example, carbon dioxide in a world, in a sea of methane, if there's life forms.
So as long as life is based on chemistry, you have some handle on what kind of byproducts it'll make.
Absolutely.
And these laws of chemistry are pretty well understood.
Yes.
Yeah, so we think we got some handle on this. So the life wouldn't be so different, like the blob or something, that it would throw you into a loop.
I wouldn't know what the bug looks like. I wouldn't know what the organism looks like, but I could tell you basically there has to be some rules of the chemistry. Yeah, that's chemistry.
Okay, good. All right, just two questions, just these last two here, okay? I'm sorry about that, but we'll be at the tables. You can come up to them. Go, Sarah.
All right, quick comment. Don, I think it was you that said the Earth has been different through most of its life, so I don't think it's fair to compare other planets to what the Earth looks like now, considering that we're in the minority of the time. Maybe you should judge against what we have been and could end up being. Maybe
I think that came up. We agreed that even Earth hasn't looked like Earth for most of Earth's history.
Yeah. And so we've been comparing to Earth-like planets as of Earth now. I just don't think it's fair. And two, we defined Earth as, or life as being, according to Darwinian evolution, given, you know, primordial ooze, or given the very early single-celled life forms that abide by Darwinian evolution, isn't more complex life eventually inevitable? I mean, assuming that no planet killer asteroid.
Everybody invokes this concept of Darwinian evolution. And it is true. It operates to a very large extent in selection. But there is another mode of evolution. It's called neutral theory. And I'll give you an example.
Neutral theory?
Neutral theory. So you have blue eyes, and people in the room have blue eyes. People in the room have brown eyes. Okay? Your visual acuity is totally independent of your eye color. There's no selection based upon your ability to see that brown-eyed people are going to have more acuity or less acuity than a blue-eyed person. So tremendous amount of variation in nature has no selective advantage, and that's just a totally non-Darwinian mode of evolution. Okay, so you and I have a life form that we have 2 arms and 5 fingers on each hand and so on and so forth, but we're not really that different from many other organisms that have similar modes of behavior. Okay, this is what makes us different in a sense. Is a very funny thing. Amongst very few mutations, we're very, very, very close genetically to chimpanzees, from which we diverged about 6 million years ago. So 3 genes, I believe, 3 mutations, point mutations, in the FOXP2 gene cluster on chromosome 7 in the human genome.
I thought it was chromosome 8, you know, I just...
allowed us to speak. That gave us speech. Okay, so that is a trivial number of mutations to give us the ability to communicate horizontally abstract thoughts with complex language. Now, that was a transformational mutation that occurred once, a singularity in nature so far. And what is fascinating about evolution...
Wait, you said it's a simple mutation that had transformational consequences.
Absolutely.
Okay.
And those are the mutations that we really don't understand what forces these singularities. They're random walks, and 1 or 2 mutations just changes the world. And that's really what the forefront of bioinformatics and molecular biology is at right now, trying to figure out what were those key freak accidents, basically, that allowed those machines to change the world.
So very interesting that you can have a life form with variation, but if it doesn't have selective advantage, it's just a variation.
Exactly.
And it's happy being what it is for 1 billion years.
Right. So there are 20 million known genes out there sequenced, And I told you only about 1,500 of them make the world go round. The rest are colors of the eyes, the color of your hair. That's the 99.999% of the genes that are.
We got to make this the last question.
Yes.
And it's a quick question, but is the answer quick? See, that's what really matters here. Go. Right here, go.
Yeah. So if we found any life on any exoplanet, roughly how much time would it take for that microbial life to evolve into an intelligent design?
There's no known answer.
How long would it take? Minutes.
I think that would depend very much on the flow of energy in that system, how much energy is available.
Suppose it has a lot of energy.
So if it has a lot of energy, that means that you can make many attempts at doing things. You can make many organisms, many replications. And
you have an enhanced chemistry experiment going on.
So I think that you cannot, I don't think you give a definitive answer to that question, but you can say that if you have a lot of energy flow in the system, it'll probably go fast. If you have very little energy flow in the system, it'll be very slow, if that helps anything.
And in your cold world on Titan, metabolic rates go slower when they're cold. Right. Maybe even if it wanted to evolve something intelligent, it would just take too long because it's too cold.
Yeah, I think Titan's not a favorable prospect because you don't have the supercharged energy system available to power large animals that we have on Earth with oxygen. So on Titan, I think you would never get beyond microbial life. On Mars, however, you could have had...
I tell you, I told you about this guy.
You were warned.
I warned you.
Yeah, on Mars, however, you could have had the buildup of oxygen very early in Mars.
Is this Mars here? Is this Mars?
That's, I don't think that's Mars. No. You could have had the buildup of oxygen very quickly in conditions suitable for supporting large organisms.
Okay, so it's quick. Okay.
Somebody said before that life, I'm going back to like the beginning, not are we finding life, but how close are we to getting life. And somebody said before it's a very complex chemical reaction. How close are we? Is it like controlled fusion? Are we that close? Or, how close are we to making this?
To making life in the laboratory.
Right.
Not close.
Not close.
Yeah. let me put it to you
these highly precise answers.
If I were to write a research proposal on I want to go and study the origins of life. I want to try to make chemical reactions in the laboratory because we don't have conditions that allow us to show the experiment can work conceptually. This is like throwing darts at a board, right? So these are highly underfunded areas of research and highly risky. One of my graduate students here is working on this and sitting right there. But the point I want to make
I'm working on it right now. Right.
But the point I want to make is that this story, where we came from, the origin of life, has been out there for a very, very long time. And Are We Alone has been out there for a very, very long time. I'm much more optimistic that in my lifetime, we're going to know Are We Alone than the origin of life.
Is that right?
I believe that.
Whoa. Wow, I wouldn't have guessed that.
I agree.
And you agree.
Go to Mars.
Whoa. Let's all thank the panel once again. Thank you. And thank you all for coming. We'll see you in the spring. And if you have more questions, you come out to the tables outside. We'll be there for you, okay? Drive safely. Thanks for coming.